Hello, and welcome to this lesson on implementing sequential logic circuits in Verilog HDL. So we're just going to jump in and see what things make doing sequential logic a little bit different than doing combinational logic, and we'll go ahead and work through an example. Let's go ahead and first actually talk about what we want to build. So we want to build a really simple sequential logic circuit. Let's say it has two inputs. Let's call them A and B. And this circuit has one flip-flop. Let's call it D. It's got its input, it's got its output, and then of course we need to pay attention to the clock, which serves as another input to this circuit. We're just going to have some XOR gates. So we'll say that A and B get XOR'd, and then we'll take that input, and we'll go ahead and XOR it again with the result of A and B as well as the previous state. And then we'll say that the output is just tied to the state. A couple things to note before we go and actually implement it. Well, first we have Z, which is just equal to D. When we implement this stuff in Verilog, we're not going to make the distinction between previous state and next state, right? Verilog will sort of take care of that for us. We'll just consider it to be one single register variable. So Z is equal to D, and we'll also say that D is equal to all three of these things. We have the opportunity here to be a little bit recursive. So D is equal to A XOR B XOR D itself, right? Since D comes back around. So these are the two primary logic expressions that we're going to want to implement. D is equal to A XOR B XOR D is equal to A XOR B XOR D, and Z is just equal to D. So let's jump into code and make it happen. So before we get started, one thing you might notice is I've got PowerShell running instead of the Visual Studio Code terminal. This is because yesterday my Visual Studio Code started being weird and started not generating the .vcd files when I run the simulations. I haven't quite debugged it to figure out what's going on there, but for some reason it just stopped doing it. So I'm going to explore that, but for now we're just going to run in PowerShell to implement our stuff. So let's go ahead and create a Verilog file. Let's call it sequential demo.v. Let's go ahead and name our module top. Top in Verilog is a lot like main in other programming languages. And we'll have A, B, don't forget the clock, and Z. And module. Now, all of our inputs are 1 bit, so we don't have to do anything special. So it's just input A, B, don't forget the clock is an input. And we have output Z. When we want to create flip-flops in Verilog, we actually can't do it with that sort of NAND gate latch structure. We can't make latches from scratch in Verilog, but what we can do is define them as reg for register. So we'll talk about in upcoming lessons. Registers are just collections of flip-flops. And so when we say reg, a 1-bit register, a 1-bit reg would just be a single flip-flop. So we'll say reg D, and we need to instantiate it with some kind of value. We'll make sure it's preloaded with a 0. And for the output, we can do a regular assignment. Assign Z equals D. So that's how we do our output logic assignment. Now to actually do the state machine part, we need to do this. The machine triggers on, or the flip-flop, triggers on the clock. So we need to set it up to trigger on the rising edge of the clock. Always at, we say pos edge for positive edge of clock. And then we have begin and end. So we could have also written neg edge of clock, which would have it trigger on the falling edge of the clock. We could have also just said always at clock, which would trigger any time the clock went high or low. But we're going to be precise here, and we'll work with pos edge of clock. Now, here we just implement that expression for D. So D is equal to A XOR B XOR D. Notice that the caret hat is the logical expression or the operator for exclusive OR. So that's all there is to it. That's all we need to do to implement this sequential logic in Verilog. Remember that output is just a regular assignment like we're used to. The register, that one flip-flop we're using, is a single 1-bit register. And then inside the always at pause edge clock is when we actually do the updating for the next state. So like always, let's go ahead and make sure and do a test bench to make sure it's actually doing the thing. So sequential demo TB or underscore TB dot V. Now let's do some of our boilerplate. Apostrophe timescale 1 nanosecond, 1 nanosecond, and include sequential demo dot V to make sure we have those modules. Now module sequential demo underscore TB. No input output parameters, so we just end the module. Now, like always, we'll do regis for A, B, and the clock. And we'll go ahead and set them all equal to 0 for a reason that will become apparent in just a second. And then we have wire Z for our output. We need that sequential demo module as our unit under test. And we'll wire up A, B, clock, and Z. Now, a thing that we're going to do that's a little bit different is instead of having everything just in our initial begin, what we want to do now is run the clock. So we'll have another block that says always begin and end. And what happens here is we're going to toggle the clock. So we'll say clock is equal to not clock. This, by the way, is why we set clock to be equal to 0 initially, right? We can't toggle the clock if it doesn't have a value in it. So we'll toggle the clock and we'll delay for 10 nanoseconds. We want to run the clock faster than we're updating our input variables to make sure everything stays in sync. Now we can do our actual test. So initial begin and end. And we need our VCD file. So we do dump file sequential demo underscore TB dot VCD. And our dump vars. This basically just says grab the variables from the test bench, sequential demo TB. Now we can do the thing. Let's treat A and B as vectors. And the sequence we want to do is this. Let's start with 0, 0, and delay for 20. And then do a little copy paste. 1, 1. 1, 0. 0, 0 again. 1, 1. I'll explain what this means in just a second. 1, 0. 1, 1. And stop. Okay, so a couple things. Right off the bat, this circuit that we've built is the circuit that we described in the sequential logic representations video. So if you're curious about the sort of state machine sequence for that, go watch that video. That's where we discuss how the data should flow through the state machine. And this bit sequence 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, or excuse me, 1, 0, lets us sort of traverse the state table for that. So like I said, if you're curious about that, go watch that sequential representations video and then come back and take a look at this. And now we're ready to go and run the test bench. So down in PowerShell, like I said, I'm using PowerShell because for some reason VS Code has decided to stop creating VCD files for me. But PowerShell or command line will work just fine. So verilog.o sequential demo underscore tb.vvp sequential demo underscore tb.v. Hey, look at that, we got some syntax errors. These modules were missing. Sequential demo referenced one time. So let's take a look and see what we got. Oh, that's because the module is called top. Even though the file is sequential demo, the module itself is top. So we need to make sure we're actually calling top in our test bench. Now let's run that again. There we go, that seems to work. VVP sequential demo underscore TV dot VVP. Now, check this out. This is pretty interesting. Because of that always begin and end business where we toggle the clock, the simulator doesn't know when to end. It thinks it's always constantly running. So we need to actually tell it to finish by typing finish in the command line, and then that finishes up what we needed to do. Type in GTK wave, and like we've done before, open a new tab, grab the .vcd, grab our stuff, and also if we want to see, so notice that we see A, B, Z in the clock. This is because at a high level, it only shows us the inputs and outputs to the circuit. If we want to see what's going on the inside, we can actually open up the UUT and see here, now we can access the register D, and we can append that guy. So right off the bat, we can see that Z and D, or Z, which should be equal to D, is working, right? Whatever D does, Z is doing the same thing. And then up here, again, go watch the video on sequential representations to see how we should traverse this state table. But we can see as the inputs are changing, the state and the output is changing correctly. So from this waveform, we're able to see that everything is working properly. You know, just for fun, what if I did that and reran everything? Ha! I was right. Okay, so we're always learning new things all the time, and even here, we're learning in real time. Maybe I'll edit this out and just have this part. No, or maybe I'll leave it in. Finish is the syntax for stopping the thing. So by changing it from stop to finish, it actually stopped my output and did the thing I was supposed to do. So here we go. Instead of stop, use finish. Some of you are probably wondering, well, shouldn't you have known that ahead of time? Other simulators in a textbook that I was reading used stop as its syntax. VVP here seems to use finish. So go ahead and use that. That keeps you from having to type finish manually inside the simulator command prompt. That is how we represent sequential logic at a basic level in Verilog, right? For our clock, always at the pause edge, negative edge of the clock, we update our registers inside the sequential logic statements. So that's how it's done. As always, if you have any questions, comments, or concerns, please let me know. And if not, I'll see you guys in the next lesson. Thank you.